Okay, I want to take a little bit of time to look through this PV diagram for ideal gases, talking about how work, heat, and the change in thermal energy relate to each other. For the case of this example, what I'd like to do is assume that NR equals 1. Okay? Let's assume that NR equals 1. So I can now say that I can get the thermal energy between the initial and the final state. And then I want to see how Q and W relate for the two different paths I've chosen here. Okay? So let's first of all write down what my thermal energy is going to be, for the change in thermal energy is going to be. So my change in thermal energy, dE, let's call it dE because I can't really do that, is going to be equal to, final thermal energy is P times V, right? Related to PV. Initial is going to be P minus the initial PV, right? Thermal energy is related to T. So a change in thermal energy is related to the change in temperature. If I'm assuming this equals 1, my bottom is just going to be PV, PF, VF minus PI, VI, which is 3 times 3 is 9 minus 1 by 1. 1 equals 8. So my thermal energy basic has increased by 8 in this process. Now let's look at my movement on this red one. Let's look at the red guy now. Okay, in this one, work equals 0, right? It's going straight up, no change in volume, so work has to be equal to 0. On this one, work, is P delta V. The pressure is 1. The change in volume is 2. So the work is going to be equal to 2 units. Okay, so I've got these two transitions. And it's going to be equal to, remember, expanding gas. So that means the work is going to be negative, right? It's the negative area under the graph, right? So it's negative 2. So if the total work done going in this path is going to be equal to minus 2 units of work, but the change in potential energy is 8, therefore, for this path, Q is going to have to be equal to dE minus all the work done, right? Equals 10 units. So there's going to be 10 units of heat pumped into this on this one. We're going to have to put in heat, 10 units of heat in order to get the final change in thermal energy from the law. Okay, now let's look at the other transition method. This one, okay, vertical one, so work equals 0. Right? The pressure changes, but there's no change in volume. Here we're changing volume, but this time at the pressure of 3. So 3 times a 2 change in volume means we're doing a work equals minus 6. So in other words, the work, there has to be minus 6 units of work to push this out, okay? To expand the volume at pressure of 3 atmospheres. We're having to do a lot of, it's doing a fair bit of work on the external area. Okay, so the pressure is increasing and the volume's increasing. Okay, the volume's increasing, so it's pushing out at 3 atmospheres, so minus 6 of work. Again, Q, then is Q plus W equals ETH. dE equals Q plus W. D equals Q plus W. This suggests that if I go on root 2, Q is going to have to be equal to, since work is minus, we need a change, so Q is going to be equal to 8 minus 6 equals 14. All right, so now basically in this route, we're requiring 14 joules of heat. This route, we require 10 joules of heat. in order to do 6, this one we're doing, and work is losing, the system is doing 6 joules of work on other things. This is where it does 6 joules of work. So you can see how taking the top one, we require a lot more heat energy to put into the system. Then taking the bottom route to get here, we require less work, less heat to be put into the system, but the system is doing more work. We could also then do them the opposite way, in which we would then be working on the system and then no work here, so 6, and we'd be losing 8, and we'd have to get how much heat we'd be getting out of the system. All right, so this gives an idea in terms of if we know how much work is, how we can then calculate how to get the amount of heat. I hope this is helpful.